Hello, our names are Yuki Qian, Ethan Poon, Eric Mittelman, Michael Manders, Enyan Perales, Arjun Nair, and Joan Miranda, and we are the Agrivoltaic team as a part of the Earth Systems Explorers. Our project is analyzing the impact of solar arrays on surrounding vegetation in agrivoltaic farming for optimization of performance. Agrivoltaics, also known as low-impact solar, is the practice of using the same land for both agriculture and solar energy production. It offers an alternative to the complete conversion of agricultural land to solar locations. This co-location practice has the potential to both address energy inequity by supplying solar energy in locations less centered on the electricity grid, while also helping farmers diversify income through land lease payments and other business models. Agrivoltaics can sustain rural farmland economies, which have an especially growing need for support. Further, only 2% of the large solar arrays in the US are agrivoltaic, highlighting the potential for growth of this practice.
The success of agrivoltaics relies on optimizing the balance between energy production and agricultural output. Solar panels can create microclimates, which can significantly affect plant growth. Our research question is, by using remote sensing tools and satellite data, is it possible to analyze the impact of solar arrays on surrounding vegetation health in order to inform and facilitate the future and success of agrivoltaic projects?
We approached this question by outlining the data of interest. Our first step was identifying agrivoltaic solar projects in the US. We first sorted through the Global Observer AOI points to identify areas with solar panels and overlaid them with the US Solar Photovoltaic Database and filtered to find agrivoltaic projects. After identifying these specific locations on the US PVDB, we matched them up with data on the Landsat database. By inputting the location into the Landsat Time Observer, we were able to identify our locations of interest and extract the data.
We then decided to use the NDVI spectral wavelengths and TCG data from the Landsat satellite to identify any trends occurring after the installation of the solar array. The NDVI estimates the amount and health of vegetation on the land. Band 4 shows the red wavelengths. Less reflected red light means more photosynthesis is taking place. The TCG shows photosynthetically active vegetation. We use the Landsat time series to allow us to access and download data from specific agricultural solar farms. After downloading the CSV files from multiple sites, it is then separated by measurement type. Then a Python program is run on the collection of CSV files to combine their data. The program starts by parsing the raw data from the CSV file. Using the construction year from the metadata, it takes a snapshot from 15 years prior to the construction to up to 10 years after the construction. This effectively centers the data around the construction year. It then averages the data from all the measurements and outputs that to be graphed in Excel.
The NDVI data showed a decrease of 18.5% after the installation of solar panels, indicating that vegetation health decreases with the implementation of agrivoltaics. Data showed that band 4 decreases by 40.6% after installation of solar panels, indicating that photosynthesis increased after implementation of agrivoltaics. This can likely be attributed to increase in red light absorption from the solar panels.
Data showed that TCG decreased by 54.2% after the installation of solar panels, indicating that photosynthesis decreased after implementation of agrivoltaics, signaling possible vegetation health decrease.
The decrease in NDVI and TCG suggests a decline in overall vegetation health and photosynthetic activity following the installation of the solar panels. However, decrease in band 4 suggests increased energy use under the conditions created by the agrivoltaic arrays. This research shows that the complex interactions between solar arrays and surrounding vegetation and will aid farmers and energy producers by contributing to the sustainable growth of agrivoltaics. In terms of future research, we expect to create an application interface to predict solar power potential or solar exposure in our area. Our tool will further optimize best land usage for efficiency in energy and vegetation growth. We also want to explore variation in agrivoltaic farms and attribute changes to conditions, such as sun angle, panel area, location, along with its relevance to weather. Determining what factors can influence values like B4 and NDVI can be essential for future research.
The best features of the C's internship was that we were able to pursue our own projects based on our interests, which allowed us to work with what we were passionate about. The main challenge that we experienced was trying to fit our research goals into the short time frame that we had.
Overall, we all reflect that the C's program both gave us insight into different fields of earth science and provided us with mentors that allowed us to explore our passions deeper.
We would like to thank our C's ESE mentors Rusty Lowe, Cassie Soeffing, Peder Nelson, and Andrew Clark, and the NASA C's program for providing us this opportunity to conduct research in this program. Thank you.
Thank you.
Thank
Thank
you.
you.
Thank you.
Thank you.